Today I'll be talking about how we can make rack pipelines more memory efficient with the help of CXL technology. So I'm Arun George. I work in Samsung Semiconductor India research. And this work has been put together along with some of my colleagues, Roshan Nair, Vikas Kumar, and Shamak Tavalai. So why we have this session? So the global AI infrastructure market is growing at a great pace. So in fact, it is expected to increase from about 46 billion in 2024 to more than 350 billion in 2032. And that's more than sevenfold growth in less than a decade. And a key enabler for this growth will be memory fabrics technologies. So when you talk about memory fabrics technology, there are proprietary standards like NVLink, UALink, etc. and so on. And then there is an open standard, which is CXL. So we believe an open standard like a CXL is very important because it helps us to explore new ideas and collaborate on different experiments, etc. So memory fabrics enable composable memory infrastructure for AI technologies, and it opens new possibilities for scalable memory expansion, flexible and disaggregated memory solutions, cost savings, and so on. So in this talk, I will highlight some interesting use cases of CXL in AI infrastructure, particularly in rack pipelines. So let's talk briefly about the agenda of the session. I will cover the basics of rack pipeline in AI use cases. Then we will cover the memory demands, some memory demand scenarios of in rack, which we are mostly interested in. Then we will talk about CXL memory pooling. And we will also talk about CXL compressed memories and how that can help the rack pipeline in memory efficiency. And we summarize with our main takeaways. So we'll start with the rack pipeline in AI use cases. So why is rack relevant? I mean, rack is a pretty popular term these days. So it's an important technique in AI workflows. We know that rack improves AI workflows. So, and it improves AI workflows, particularly large language models. So, while LLM are excellent in generating content through NLP, natural language processing, they tend to hallucinate when asked about the data which they haven't seen yet. Maybe it could be some up-to-date information, or it could be some domain-specific information. So it could come up with some made-up information which might not make sense or might not be relevant. So RAG is a solution for those use cases. So we can say that RAG acts as a framework for LLM to provide more relevant or up-to-date information while generating the response. So we will cover the RAG architecture in brief. This will set the foundation for our upcoming slides. So in short, we can say that a RAG combines retrieval with generation. So G in RAG indicates the generation, which is the LLM model part, which generates text response for a user query. The RA part indicates the retrieval augmented part. This is the part which brings the differentiation. So it means instead of relying on what the LLM has been trained so far, RAG provides some additional context to tune the models and responses. So this is the part which avoids hallucinations. So if we look at the diagram on the right side of the slide, you see there are two stages for the RAG pipeline. The first stage, which is the data ingestion stage, it's a phase where your local data or local documents or domain-specific information that has been processed and converted into vector embeddings and then fed into a vector database for future retrieval. So the second phase is the query phase, where the user generates a query. So here, instead of directly feeding the data to LLM, the RAG pipeline does a semantic search on the vector DB thing, which we have already fed. So we get some results, and we use the results as the RAG use the results as the context for further search. So now the query is now augmented with this additional context we got from the vector DB. So this question plus context is fed into LLM model, which could now give a more relevant answer for the questions. So now let's move into the memory usage scenarios of RAG, which is the main context of discussion in this topic. So we could observe two clear memory demand scenarios and more transient memory demand scenarios, I would say. They are with respect to vector DB use cases mostly. The first one is in the memory ingestion phase, where the processing of local knowledge takes place. We can say that huge memory is required for the creation and parsing of vector embeddings in the stage. The second part which we are interested in is in the query phase, where the vector DB engine is subject to queries. So depending upon the workload and the rate of queries, that might also face some transient memory demands. So now we have established the case of the situation of transient memory demands in RAG pipelines. Now let's see some potential solutions. So we can see the case for a on-demand memory here. So what we really need is a memory that we can borrow when the workload demands it and release when the work is no longer required. That's what we actually need. So this is where CXL comes in. CXL technology could be a great fit for this problem. In particular, CXL memory pooling gives us that exact flexibility, the ability to provision memory on demand and release it when dynamically when not required. So now let's move into the CXL and CXL memory pooling part. So we will start with some few basics about CXL technology here. This is again to set the foundation. We will not go much deeper. So as we know, CXL is an open standard interconnect for memory fabrics use cases. So it's designed for high-speed cache coherent communication between process, memory, and accelerators, and so on. So more importantly, it's designed to reuse the existing PCI physical layer, which makes the adoption much easier. So as the diagram shows, it could be either connected through a switch in which it can share the CXL bus with other memories, accelerators, and so on. Or it could be directly connected through an expander. So it's also interesting to see how CXL fits into the existing memory hierarchy in terms of latency and capacity. So CXL is envisioned to fit in between DRAM and SSD in the memory hierarchy diagram. Its latency is a bit higher than DRAM and maybe slower than, the latency is better than SSD. And in terms of capacity, it might have bigger capacity than DRAM typically, or the capacity might be lesser than an SSD. So that's how it's envisioned to fit into memory hierarchy diagrams. So this is where we get into the details of CXL. I will skip most of it. So the core idea here is that in CXL bus, different kinds of devices could exist, like memory devices, accelerators, and processors, and so on. So they all have different capabilities, and some have cache coherent memories, some are just memory expansion devices. To support all of them into CXL bus, it defines different kinds of subprotocols, and also it defines different kinds of device types. These are meant to support different kinds of class of devices which are meant to fit in CXL bus. So now let's move into the concept of CXL memory pooling. So there are three key aspects to be noted when we talk about CXL memory pooling. The first thing is disaggregation. So CXL enables disaggregated memory access. So you can access a remote memory as if it is a local memory, though albeit with some extra latency. So there are workloads which are okay with that extra latency. Those can make use of it. So it means it enables on-demand memory expansion by making use of the disaggregated memory, possibly from a common pool. Then comes the point of resource sharing. Some memory resources could be shared among different hosts, either at the same time or in a time shared manner. So Another key point is dynamic capacity manager. With CXL, you can expand or shrink capacity neatly. I mean, CXL already supports memory pooling from version 2.0, so that sets the foundation for the basics of memory pooling. And then now it supports dynamic capacity devices from version 3.0, which will support this memory expansion and release in a more gracious manner. So, since we covered the basics of CXL memory pooling, let's cover a few more points about the rack plus CXL solution. So, we already mentioned that the vector DB use cases are the most interesting ones here in the rack pipeline. So, particularly the insertion stage, where it requires a lot of memory, large amount of memory is required for the insertion stage. So, that's what we are mostly interested in. And we use some benchmarking scripts to conduct our experiments. We used MLPerf storage benchmarking scripts from ML commands. And we used Milvus DB, which is a popular vector DB thing. And we used DiskKNN algorithm. We chose DiskKNN over other algorithms for our experiments because we could get more transient memory scenarios if you use DiskKNN, because DiskKNN uses the RAM temporarily. It loads the vectors in RAM before flushing it to disk. So we will have more transient memory demand scenarios. So other point that is worth discussing is about the CXL 3.0. And the CXL 3.0 is very promising, as we discussed, because it supports DCD. The actual hardware support is slowly arriving. Some of the hardware support is not there yet. It's not widespread yet. So we chose QEMU-based emulation to prove the solution quickly and conduct our experiments. So this is a setup we used for verifying memory, CXL memory pooling in the rack pipeline. So the key point here is that we used a hypervisor VM setup to create the experimental scenario. So you can see that an MHSLD multi-headed CXL device is emulated in the QEMU, in the hypervisor. So there are three VMs performing different roles of the rack pipeline here in this setup. So the VM1 or the host one, which is the data ingestion engine. So it parts the documents and create vector embeddings. So we have run MLPerf storage benchmarking scripts to achieve the same in VM1. So the VM2 or host 2, which is a vector DB instance, runs the DB engine and processes any incoming request. So you can say that VM1 issues the request to VM2 or host 2. Now for the insertion stage. So now we have the VM3 or host 3, which runs the query generator. It's a more of a runtime things. Now we have memory monitor agents running in VM1 and VM2 to monitor the memory and inform the orchestrator. There's a memory orchestrator accordingly. So the orchestrator is more like a miniature fabric manager of CXL. So it runs in the hypervisor. So it helps the hypervisor to provision memory on need basis on VM1 or VM2 on need basis, and it could help to expand and release memory on need. So, okay, and other point to be noted is the memory agents communicates to orchestrator by means of gRPC, and the orchestrator configures the QEMU instance by using QMB, out-of-band communication mechanism. So, yeah, and as we discussed earlier, we use DiskKNN algorithm in vector DB, and we also use SSD because we used DiskKNN. So now we come to some of the data from our experiments. So this particular data is taken from a data ingestion engine while the stage 1 is running. So there are two graphs over there. The bottom one, which is the orange line, which shows the memory use, actual memory usage of memory. The upper one is the actual memory provision. Provision includes DRAM and CXL. So as we spoke earlier, the memory monitor agent script keep a watch on the amount of memory available in the system. When the availability goes below a watermark, so memory orchestrator is triggered and more memory is provisioned. So you can see here that in the beginning of the graph, as soon as we start the stage 1, which is the vector creation stage, the memory usage goes high, which is the orange line, and as a result, the memory availability also goes low below the watermark, and then the more memory is provisioned through orchestrator. And the total memory availability goes high. Now we can again see that as soon as the stage 1 is finished, the memory usage goes low. Now we have another watermark which checks for the the memory availability in the system. If it goes above one watermark, we start releasing memory. So you can see that as soon as the stage 1 is completed, the memory orchestrator, which is the miniature fabric manager, start releasing memory, and the memory availability and usage goes back to normalcy. So we also see in the results from the VM2, which is the vector DB instance, also from the same stage, which is the data ingestion stage, first stage. So this is the stage. This is a instance which is subject to a lot of insertion queries from the VM1. So you can see that as soon as the insertion starts in the VM1, here the VM2 is the memory usage also spikes up, and as the memory usage spikes up, and then the availability also goes low, and immediately more memory is provisioned. So you can also see that it goes down also immediately. This is because we use disk-ANN algorithm, which uses the DRAM spontaneously and then flush the vectors back to the disk. So it goes on for some time, and eventually the stage 1 completes, and the extra memory is also released. So you can also note that the memory expansion and release goes in batches here. This also because the stage 1 actually happens in batches. So the memory expansion and release also works in tandem with that particular stages. So if we have some words about the setups as well. We used Kemu with the MHSLD patches. I mean, it's not. I think it's not integrated to the mainstream, but we took the patches from open source and applied. Same for Linux kernel. We have taken the DCD patches from the Linux MM mailing list and applied to kernel 6.12. And we used a Milbus vector DB, which is available as a Docker instance. And we also took the scripts from ML commands. So the key message here is that all the support is available in the open source community. Some are merged, some are yet to be merged. But if anybody want to experiment with CXL 3.0, all the software support patches are available in open source community. So it's important to talk about the TCO benefits of such an approach. I mean, we explored the CXL memory pooling for the rack pipeline. So what's the benefit? And we certainly have TCO benefits. Our estimate is that it could result in 41% of TCO benefits with the memory pooling approach in rack pipeline. So for our experiments, we required 80 GB of local DRAM. Without CXL pooling, we required 80 GB of local DRAM for the insertion host, which is the VM1, and 16 GB of local DRAM for the vector DB instance without VM2. So when we apply pooling, it could be brought down to 48 GB from 80 GB for the insertion host, and 8 GB for the vector DB, from 16 GB to 8 GB. So, and also for this calculation, we have not considered the setup cost for the memory pool. We assume that it can be ignored if the solution is deployed in a large-scale fashion. So the key takeaway for us is that CXL-based memory pooling enables smart memory management solution in rack with certain definite cost benefits. So that's the key takeaway for us when we deploy memory pooling in a rack pipeline. So with this thing, we will move to the next approach, which we have experimented in rack pipeline. So this is another mechanism for CXL memories, which is an upcoming proposal. It's about CXL compressed memories. So last year there was a proposal in OCP about hyperscale CXL tied memory expander, which is nothing but CXL compressed memories. So in particular, it talks about CXL memories with inline compression feature. That means some of the data in the memory device could be internally compressed by the device without the obvious knowledge about the host. It's transferred to the host. So host need not have to know about the level of compression in the device and so on. So interestingly, there are two aspects to it. The first aspect is that memory capacity overcommitment. It means the effective memory capacity of the device can be now increased by the compression. So it's kind of a thin provisioning, you can say. So let's say the actual capacity is 1 terabyte. Maybe if the device is doing a very good job in compression, so the effective capacity could be made 2 TB or 3 TB and so on. So the host will be able to see the effective capacity in the physical address space instead of the original capacity. So the how and how that capacity is expanded and released is under discussion, still under discussion. There are different mechanisms being discussed right now. So that's one aspect. Second aspect is about variable access latency. So you have certain memory locations which are compressed, which are non-compressed. So when the host is accessing the locations which are compressed, the device has to decompress and give it back. So these locations would incur some certain higher latency than maybe if the normal CXL access latency is around 250 nanosecond, this the latency on accessing the compressed locations would be around 1 microsecond, something in that sort. So the host workload should be tolerant for that. I mean, there are certain workloads which can tolerate this kind of higher latency. So it's meant for that kind of workloads. So in short, this kind of a proposal or this kind of an approach results in a number of clear benefits. The memory can be expanded without any additional cost. So you have the same physical memory, but you do some magic stuff in the device and the resultant capacity can be expanded. So it can give TCO benefits if used in the right use cases. So maybe this kind of memory could be used in the cold data workloads and so on. So the key takeaway here is that maybe the compressed memories provide memory overcommitment, which helps in expanding the memory and can result in certain TCO benefits. That's a key takeaway that we can take from this proposal. Now let's explore the use of compressed CXL memories in RAG use cases. So we know that it enables cheaper memory expansion and gives more headroom for memory demand scenarios. So maybe certain scenarios in RAG pipeline would be better than other scenarios. So maybe in particular vector DB insertion and both query phases could be benefited, but maybe the insertion phase could be benefited more because it could be less latency sensitive, we could argue. And maybe the most of the data is accessed only a few times in the insertion phase. So our takeaway here is that compressed CXL memories could help the memory demand scenarios of RAG. Some stages more and some stages less. So we did some experiments to verify our understanding and arguments. So we just wanted to see if RAG could be benefited by compression. So our setup included a CXL device simulation using a CPU-less NUMA memory. We kind of emulated, for this experiment, we emulated CXL using a CPU-less NUMA memory. We just disabled CPU cores on a certain NUMA node, and assuming that this will give a comparative latency and functionality similar to CXL memory. So now we needed to do a compression feature similar to a compressed CXL memory. So we have achieved that through Linux ZRAM feature. So ZRAM in Linux kernel provides a compressed swap backend on RAM. So this setup could help us to verify the effectiveness of compression in this kind of workloads, RAG workload or any other workload. This setup could be used to verify the effectiveness of compression in any workload for that matter. So to make our setup more perfect, we made ZRAM to work only on the emulated CXL memory for this experiment. So this setup now looks more closer to a CXL compressed memory, you can say. So initially we did the experiment. We ran a vector DB instance with 10 million vectors and we used a certain amount of DRAM and CXL, 64 GB of DRAM and 64 GB of emulated CXL DRAM. We could obviously see that this workload actually requires much more memory than available. I mean, not much more than 128 GB of memory. So because we got into out of memory situation and then the vector DB bench process got killed. Now we did the second round of experiment, which is with compression. So we run the same setup with our compression enabled by means of Linux ZRAM on the emulated CXL ZRAM. So we were also observing the effective capacity by means of compression. So we could see that our effective capacity of CXL goes above 80 GB. It could go much beyond that. So compared to the 64 GB earlier, the actual physical capacity, and we are able to run the vector DB benchmarking instance successfully. So this experiment was conducted to verify the effectiveness of compression in certain workloads, maybe, and we also want to verify if the workload is impacted by the slower latency and so on. So we have certain takeaways from using CXL compressed memories in RAG pipeline. So one of the takeaways about memory expansion, it enables memory capacity expansion in a cost-effective fashion. So latency, it is useful for non-latency sensitive scenarios, maybe, and maybe not all workloads would be benefited. So there are certain workloads which are obviously non-latency sensitive. So maybe the third point is about scalability. Maybe it enables a scalable memory expansion, maybe by using cheaper memories over CXL bus and so on. So now we summarize with our key takeaways. We have explored two approaches. One is CXL memory pooling, and second thing is CXL compressed memories over RAG pipeline. We summarize the key takeaways for both approaches. So we have seen CXL memory pooling first. It handles transient memory demands. So it could effectively handle transient memory demands, particularly in the stage one where huge amount of memory is required for a short amount of time. So CXL memory pooling is an effective scenario for that kind of situations. So second scenario is about CXL compressed memories. So with this approach, we could expand capacity cost effectively. So it provides TCO benefits with using by means of a cheaper memory, you can say. So the key point is it provides memory expansion. So third point is both solutions give us TCO benefits in different ways, but both solutions could help us to do TCO benefits. And the fourth point is about scalability. Both solutions offers us scalable solutions, which could be achieved with the cheaper memories or normal memories and so on. So maybe we can say that the overall learning for that CXL opens up maybe new possibilities for building more memory efficient AI pipelines, maybe in rack pipelines and maybe in more workloads such as rack. So that's all about this session, and thank you for attending. And any questions, please?
A couple of questions.
Yeah, sure.
What's the recommended ratio of CXL to main memory?
Okay, I'll repeat the question. The question is about what is the recommended ratio of CXL to main memory. So right now, I don't have a right answer for that. Maybe. Okay. From software perspective, it's okay. I mean, it's okay to. It depends upon the workload. So, in the workload that we have used, we used 1:1. So, and the CXL memory it could be expanded from 1:1 to maybe 1:2 and so on. So, I guess it depends upon the workload, I would say.
And then my second question on cheaper memory.
Okay.
Are you suggesting DDR4 or CXL or what? How do you come up with the statement cheaper?
Okay, fine. I'll repeat the question. I mean, the question is about the cheaper memory. So what do you mean by cheaper memory is the question. So I didn't mean any particular thing. It could be even compressed memory. I mean, with compressed memory, you could actually increase the effective capacity. So it could be anything. Maybe, like you said, DDR4, reuse of DDR4, right? So it
Compression gives you less expensive.
Yeah, exactly. That's what I meant. Yeah. Okay, yeah.
So I didn't quite get it. When you said you emulated the CXL MHSLD
Okay.
using KMO,
Yeah.
you just use like a dual CPU and the other CPU's memory was used as CXL to simulate the extra latency. And then you use some KMO mechanism to
Okay.
locate your VM. The VMs are running on one host, correct?
Yeah, exactly. So I'll repeat the question. The question is about MHSLD simulation. So we did not emulate this latency. We just emulated the functionality here. So it's just a hypervisor and which runs multiple KMO VMs. All right. Okay.
One of the VMs was just to do a memory allocation.
No. Okay. So you're asking about the exact functionality of about the VMs, right? So the VM.
You showed 3 VMs.
Right.
And there was a fourth something below.
I'll just go over there. Yeah.
Yeah, this one.
Yeah.
CXL Type 3 MHSL.
Yeah.
How did you do that to have that?
Okay. So there are certain implementation in KMU about the MHSLD implementation. So it takes memory from the hypervisor, certain hypervisor.
From the local DRAM.
Yeah, exactly.
They just simulated the ones.
Yeah, right.
Yeah, I'm going to use the same slide in my talk coming up at 4:30.
Oh, great. Okay, nice. Okay, yeah.
Whatever he asked, David asked.
Okay.
I have an example for that.
Okay.
4:30. I'm Anil Gorvale. I'm representing the CXL consortium.
Oh, great. Nice to meet you. You have a question?
How are you calculating TCO? You said that there's a 41.6%.
Yeah. Okay. The question was, how do you calculate the TCO? It's just a calculation of A by B. I mean, normal calculation. We just calculated how much of memory we could reduce from the. I'll go to the slide anyway. From the local DRAM usage. So earlier we were using 80 GB of 80 plus 16 GB, and now we are using 64 plus 8 GB. It's just the ratio.
Okay, just the ratio of power consumption.
No power consumption. The memory usage. It's simple calculation. Okay. I guess that would be it. Yeah. Thank you.